Thanks for coming to my talk. So we're going to talk about shifting left and how shifting left also means zero trust. I think I have about 15 slides, so probably going to blitz through the content and ensure that there's enough time for questions as well. Okay, so moving on to the next slide. Yeah, this is a quick introduction about myself. I currently work for AMD. Previously worked at Athena Health, Bain, Bose Corporation, and also Northeastern. My areas of interest are DevSecOps, distributed systems, and applied AI. Feel free to connect with me on LinkedIn and GitHub. Yeah. Moving on to the next slide. All right. So from an agenda perspective, I think we're going to spend the first few minutes defining what zero trust is, which some of you might already be aware of. Then we're going to talk about why we need zero trust at the API layer and what are the key pillars of zero trust are. Then we're going to talk about some standards that help us implement zero trust, like SPI, FFE, and Spire. And that's going to be followed by a quick demo where we're going to use Istio and a few other tools to ensure there's mutual TLS everywhere, and we're going to actually see the serverless mesh in action. And we're probably going to talk about some anti-patterns and best practices. All right. Moving on. So if you look at zero trust, it essentially comes up from the term where you want to solve a bunch of cybersecurity challenges where you are sort of moving defenses from network-based parameters to users, assets, and resources. So instead of solely depending on particular assets, physical or network location, or like asset ownership, you sort of try to protect resources not just based on network segments, but sort of like make it much more broader. Because earlier, I think it was more about as when two different services talk to each other, the primary point of zero trust used to be like the network location, and it's no longer seen as the prime component of the security posture that we envision. And from an enterprise perspective, zero trust is a response also to network trends where you end up having cloud-based assets that are not located in enterprise-owned networks, and even from an authentication and authorization perspective, you also want to ensure that there is you always ensure that you never trust and you always verify. Moving on to the next slide, when we look at the key pillar. When you look at the key pillars of zero trust and why zero trust is essential at the API layer, in today's modern world, I think whenever you end up building any application, the first thing you probably want to expose to the user is a bunch of APIs. And 83% of the traffic in microservices is internal east-west. So what I mean by east-west traffic over here is it's within the data center or within the cluster. And northwest traffic would be coming into the cluster from an external point. So imagine like a typical example of an east-west traffic would be like microservice A talking to microservice B, and both of them are in the same cluster or availability zone. And imagine there's a database. There's also like there's a cache or a pod running in AC1, and there's another pod running in AC2, and they're trying to talk to each other. That would pretty much be like east-west traffic. Whereas if you have an end user trying to talk to an AWS API gateway, or like say, or like a partner system that has a public endpoint, that would be like not so traffic typically. And from a zero trust perspective, I think we want to ensure that both east-west and both east-west traffic and north-south traffic are considered equal, and I think we want to ensure that we implement all the zero trust principles for both of them. I think we will touch upon this a bit more when we extrapolate this to multi-cloud environments, but I think that's it for now. And if you had looked at, why this is important in the API layer, and if you had looked, when you reference open source projects like OWASP, there are a bunch of API level vulnerabilities. For example, there's security misconfiguration, server-side request forgery, broken function level authorization, and a bunch of others which demand zero trust to be implemented at the API layer. And from an industry perspective, banks, retail, transportation, IoT, all of them have started implementing zero trust principles at the API layer. Sometimes, and previously when I had worked at a regulated industry, sometimes API can also expose personal identifying information, and or rather known as PII. And such APIs have made it increasingly have rather extended the attack surface of how APIs can be targeted, and that's why zero trust implementation of zero trust at the API layer is fairly critical. Cool. So when we look at zero trust at the outset, there are about 3 or 4 characteristics. One is every workload must have a verifiable identity, which is characterized as strong identity. And second is least privilege access, which is services should only talk to other services that they absolutely need to. And followed by continuous validation, which is we shouldn't check if something is as expected, say once during login, but we should keep checking the behavior so that it adheres to the baseline that we have set. And finally, we also need to ensure that the entire pipeline or workloads have a lot of visibility in logging, because you can't secure what you can't see. So from a demo perspective, I've tried to spin up a GitHub repository or a live demo that uses a variety of tools, and it tries to convey the various the importance of zero trust, and also addresses why each layer, be it identity, transport, authorization, visibility, and gateway, are important in trying to implement zero trust from a boot up standpoint. So I in fact call my GitHub repository as zero trust boot up for people for somebody who's trying to familiarize themselves with the zero trust principles. Oh, and regarding to tooling, for identity, I've used Spire and SPI FFE standards. For authorization, I've used OPA and some basic Rego policies. And for transport, I've used the Istio Service Mesh Gateway, which helps in implementing MTLS. And I haven't done a lot of visibility in the current demo, but the architecture can be extrapolated to ensure there's visibility, and it can be tools like Prometheus and Hager can be used to ensure that there is enough metrics and traceability. But we will also be looking a bit more deeper into the gateway, how the gateway and the HTTP filters are set. Just doing a quick time check. So. So I just wanted to introduce what SPI FFE and SPI RE are, and then we could probably jump into the demo. So SPI FFE stands for Secure Production Identity Framework for Everyone. It's a set of open source standards for securely identifying software systems in dynamic and heterogeneous environments. Before I probably blitz through what SPI FFE and Spire are, has anyone already used SPI FFE before, or is this the first time you are hearing about it? Oh, you have, okay. Oh, you have not, okay, cool, okay. Thanks. No, I just want to know if somebody has already has used SPI FFE in production, and if they're familiar with it. Okay, so systems that adopt SPI FFE can easily and reliably mutually authenticate wherever they're running. And conventional security practices like network policies that allow traffic only between, say, 2 VPCs or a particular IP addresses struggle to scale when the complexity rapidly increases. So what SPFIE does is, it's a set of open source specifications for a framework that's capable of bootstrapping and issuing identity to services across heterogeneous environments. And to put it in simple terms, the heart of these specifications is that there is a short-lived cryptographic document called SWID, and which is a simple API, and the various workloads running in different data centers, they use these SWIDs as identity documents to authenticate across workloads. For example, to establish a TLS connection, or by signing and verifying a JOT token. So SPIFFE is like a standard that helps you identify various actors in play, and Spire is essentially an implementation of SPIFFE. There are various ways to implement SPIFFE. In fact, the Istio service mesh is also one of the means to implement SPIFFE, and a lot of other players have implemented SPIFFE in production. For example, GCP, Google Cloud use SPIFFE, GitHub, GitLab, Atlassian. If you look at, if you look at all the engineering blocks, all of them pretty much adhere to the standard. Cool. What Spire is, just to give a heads up on what Spire is a production-ready implementation of the SPIFFE API, and it performs node and workload attestation in order to securely ensure that the SWIDs are registered and the SWIDs are verified, and they follow a preferred set of conditions and for the workloads that are under play. And probably can move on to the next slide, and then quickly talk about the next few slides are going to talk about how the Spire server and the agents are set up. So they have a plugin architecture where the server itself has a data store plugin, a key manager plugin, an upstream authority, and a node attester. The data store plugin and the node attester are essential because the node attester ensures which are the various agents that are registering with the server. The data store, of course, is the persistent storage that holds all this information, and there's also like a workload API by which various agents can request for the SWID to the server. And this is the agent. It has a very similar setup since it has the plugin architecture, and there's a key manager that ensures that takes care of the authentication and stores things in a persistent storage. There's a node attester which again ensures that things are it does the due diligence of registering with the server, and all the various workloads that the agent manages, or possibly possibly one agent can manage a bunch of other agents, and they are essentially they talk through the workload attester. Yeah, probably blitz through that. We'll probably unpack them when you're actually looking at the demo. So why do we need mutual MTLS and Spire and Istio everywhere? They provide authenticity of services. They ensure that all the communication have encrypted transport, and anything that comes into the service mesh and also goes out of the service mesh is absolutely secure. So maybe I can spend a bit of time talking about what Istio brings into the demo and why we need to care about it. So Istio is an open source service mesh that layers transparently across different applications, and it helps in this particular demo. It probably also helps in distributing the cryptographic identity document called SWID to the various agents, and it also helps in service-to-service authentication, load balancing, monitoring, and it supports various protocols like HTTP, GPRC, WebSockets, and so on. And it's a pluggable policy layer, and it supports and you could also like plug it in with logs, traces, and traffics within a cluster. And why we need to care about MTLS? I think this is fairly familiar territory. It relies on asymmetric cryptography to prove the identity of a sender and recipient of a message, and it also asserts that the message has not been viewed by a third party. So if someone is interested in implementing zero trust at the API layer, and how do they get started with that? Again, a quick question to the audience. How many of you work with Kubernetes on a day-to-day basis? Okay, so this is fairly new territory. It's great. So we're going to have a lot of takeaways. So to actually implement this as a quick demo, I ended up just moving windows. I ended up creating a small workload. So if you look at the code here, so I pretty much have like an echo service which basically says hello. It's like a hello world, right? So it's pretty much like a Flask server that basically tells you like hello, and that's pretty much it, right? And so what happens here is while execute the code, we have an external client, and the client essentially sends an MTLS request, and the MTLS request goes to something called an envoy. The envoy is a sidecar at the user service layer, and the envoy essentially decides what to do with that request. So let's unpack it layer by layer so that it gets easy to understand. So when the request comes in, this is the envoy.yaml. The envoy essentially passes the external API request, and it essentially calls an authorization filter, right? So if you see line number 31, it calls an authorization filter through external authorization, and the envoy and this filter type essentially is configured where the open policy agent listens. What the open policy agent does is it receives a JSON document, and that contains like headers, method, path, peer certificate, the SPFFI ID, and it essentially runs a policy on the API request. So you can set whatever policy you would like. Like for example, the policy that I have set over here is it should be a GET request, it should come from an admin, and then it's essentially like path based. It can be like coming from a user, right? We could have complicated policies over here defining like who is allowed to request the server, who should not be allowed to request the server, and so on and so forth. But essentially the key takeaway is when an API request comes in, it hits the sidecar, and the sidecar essentially passes the request and then the open policy agent applies all the policies on it, and then once the Rego policy is run, the policy essentially is shipped to the open policy agent as a bundle, and it sends a response, and then if everything looks good, either forwards a request to the application container by returning a 403 or a 200 if everything's okay. So that's the demo, but I'll show you how the demo is. And doing a quick time check again. And the real advantage over here is that we only have like from a Kubernetes standpoint, we only have like one pod per sidecar, and so there is enough isolation between each like we have multiple teams defining different APIs. You have enough isolation between each service or team, and there's horizontal scaling where OPA scales with workload replicas, and there's only one OPA agent per node, and so there's very little overhead. And there's a central, and since it's a central open policy agent service, you can have it's a single source of truth to manage policies. So, I mean, there's a lot of there's a lot to unpack here, but the overall the TLDR version of it is the Envoy sidecar enforces encryption, routing, and retries. The open policy agent decides what to allow and what to deny, and through the HTTP filters that have been set, and they all talk over HTTP or GPRC, and the latency is like fairly very minimal. Okay, so I can probably move to my terminal. I mean, I wanted the demo gods to be really kind to me, so I ensured that I ran this stuff and did not close my laptop before the talk. But that being said, maybe I can just quickly glance over here. So my actual workload is the echo.yaml, and the entire SP IFFE standard that I probably talked about in the previous slides have been implemented through in this folder called the Spire folder, where I start a Spire server and a Spire agent, and this is the YAML file to manage the open policy agent. And if you notice over here, I basically said allow everybody, right, for now, but you could tinker with it and then set up custom Rego policies to define how you do not want to allow certain acts, and this is the service mesh implementation. So that's a bird's eye view of how the repo has been set up, and for the demo I'm essentially using Minikube. I'm not actually using an actual Kubernetes cluster. So if you do a kubectl of get pods, I have an echo service, which is my actual workload, and the Envoy gateway, the service mesh, and the open policy agent, all of them are running. And something else that I could also show is this is how the config of the service mesh looks like. So if you see here, this is the HTTP filter, and I basically said that if the OPA server is somehow unreachable during this demo, I basically told it to allow for failures. And this is essentially the policy of the OPA policy. It maps to the example.rego file, and the actual SVID IDs can be seen through this line. So based on the number of requests I did, every request is having a SVID ID, and there's a valid from, and there's an expiration time, and so on and so forth. So I mean, the demo itself is like fairly straightforward. Like if I just curl, I'm going to get a 200 OK, and if I probably say I'm user Alice, I am probably going to get much more verbose output. But that's pretty much it. But the overall takeaway is how this whole thing has been set up, and how it can be extrapolated to something much more complicated through and how the various zero trust principles have been set up. So we're using the service mesh to ensure that there's enough. Using the service mesh in combination with the SPAFFE standard, along with the various workloads, all running in different pods, through which we are directly applying the zero trust principles. Doing a quick time check again. So yeah, so each pod over here is going to get its own SPIF ID, as I mentioned, and there's going to be service-to-service encryption, and there's going to be like policy decisions made by the open policy agent, and this is essentially like north-south entry, because me being sending a request from the terminal is an external request going to the service mesh. So what you right now saw here was like north-south traffic. Okay, going back to the slides. I think I have probably like another 7 minutes. Oh, by the way, if you scan the QR code, you get access to the entire code. Yeah, so it's pretty much open source. You can probably pick it up. So why does all this matter? Like, why does SPIF matter, and what's the whole deal with it? Is when you have like a hybrid multi-cloud environment, say you're working in a company where you're doing, like one of the previous companies I'd worked for, they had this whole digital transformation journey where they were moving from ECS to EKS, or they were moving from Azure to GCP, or like Azure to AWS, and so on and so forth. So you can, and when you're doing that, and let's say you also really care about like security, you can move workloads across different Kubernetes clusters or between clouds without changing the way how identity is issued across the various workloads. So every workload that you care about also gets us like a SPIF ID, and there's no shared root certificate authority. Each cluster has its own certificate authority, and only the public bundles are used. And there's fine-grained open policy agent policies, and the open policy agent policies also run on separate pods. They can also be run on different availability zones, by which the policy themselves can be scaled without touching the application code at all. Yeah, so this is an example of a multi-cloud setup where we have a similar setup, where we have in AWS we have like a user service, and in GCP we have a billing service, and the communication between the user service and the billing service would be like an east-west traffic, whereas the coming from the API gateway would be a north-south traffic, and each of them could have their own SPAFFE standard implementation and SWIDs, but since the issuing authority of SWIDs are federated, they sort of like know each other, and this is one possible implementation of how it would be in multi-cloud. Doing a quick time check again. Something else I also wanted to cover was just walking through a quick example, since we have a bit of time. If you have like a browser or an external app, and that would essentially hit the API gateway, and that would be like the north face of the mesh, and it would handle all the external traffic like TLS authentication and so on, and then would ask the OPA for a policy decision, and that would enter the service mesh, and like the whole idea of implementing SPIF ID, ensuring that there are SPIF IDs and authentic and identities verified between the AWS cluster and the GCP cluster is because you never want to assume the internal network is also safe. And the whole idea of zero trust is about not looking at it from a network segment perspective, but more of a user and asset perspective. So if you ask like what lives in each cloud, the Spire and Istio control plane components live both in the AWS and the GCP, but they would have their own trust domain. I think I just wanted to highlight that difference. Yeah, so moving on to the next slide. I hope you had the key takeaways that, I mean, when we generally talk about security, it's all, previously it's always been about software bill of materials or ensuring that, or taking it to the left by ensuring that you integrate security tools with your IDE and, you capture vulnerabilities at an earlier stage so that they actually don't get into production. Some of the famous vulnerabilities are like Log4j incident and a bunch of others. But I think the key takeaways from this talk would be like that the APIs themselves are the new trust boundaries, and while we define and implement the APIs, we should care about how we implement security at that layer. And zero trust is about identity, policy, and visibility. And SPIFFE and or Spire plus service mesh is just one way or one means to that robust foundation, right? So my GitHub repo is just one example of how this can be implemented. There are probably several other ways to do it. If you actually go into the OWASP project or the SPA or the Spire project, they have different ways of implementing the same thing. And we always have to design with east-west and multi-cloud in mind because cloud environments can always be dynamic in nature, and having this mindset helps you to be susceptible to various changes. And yeah, so with probably end with this slide. So if you look at my actual demo, there are a few things that can be improved. Just wanted to highlight that as well. If you eventually get eager and look into the code and check it out and try it out yourself in your laptop. Things are like fork my repo and then contribute to the repo as well. Things that can be done are, so I only had an open policy agent policy, but open policy agent policies are just doing like simple path based checks. If you look at it, like if you remember the request I sent, I was just basically saying like I'm Alice and I just hit the hello server. But you can have like attribute based access control, which helps you to leverage JOT and helps you to assert like roles, tenant IDs. You could even have like risk scores based on that. The Envoy service mesh I used didn't have a rate limiter, so you could play around with like layer 7 controls and ensure that people don't really abuse the API itself. You could also like integrate GitHub Actions and ensure that kubelint and kubeconfirm are integrated into the workflows, so that you catch like errors in verbs when you set RBAC policies, or like or you like when you touch like privilege pods and so on. You could also like, I think I mentioned this in passing, you could also like integrate with Prometheus and Jaeger, where you care really about metrics and then probably export it to like a Grafana dashboard, care about like how APIs, which APIs are secure, which APIs are unsecure. You could even like have a clear idea about the various call graphs and so on. And talking about call graphs, you could also have like AI models to not really complicated ones, but just lightweight models that understand like request volumes, latencies, and if there's any deviation in spikes, it basically raises an alert. And then yeah, so you could have like simple percentile based thresholds, ensure so that you catch like 80% of the bad stuff at the API layer, and then probably integrate with like advanced ML techniques if needed. But so together, I think this whole repo and probably this demo and probably also introduced you to Kubernetes, but at the end of the day, it ensures that the various zero trust pillars like strong authentication, authorization, runtime hardening, continuous validation, rich telemetry, identity are delivered incrementally so that teams can add zero trust at their own pace. So the whole point of the talk was to ensure that an architecture for implementing zero trust from first principles is introduced, and that can be extrapolated as needed. I hope that sums it up, but cool.
All right.
I think I was at time.
Thank you.
Thank you.
Yeah, thank you.
One question.
Yeah, quick question. So it's a very nice suite of tool set here. Do you have any experience in implementing this in a large scale where you can provide a admin interface to distribute policy authoring across enterprise? So not all policies are managed centrally, but you can also distribute local policies based on the products, right?
Right.
So is in this tool set, I don't see any authoring tool, the policy authoring tool or the governance tool there. So do you have any experience?
Yeah. So yeah, that's a great question. Thanks for asking. So if I understand your question right, you're asking at a very large scale, how do you manage policies at that scale, and also is there a leeway into also introducing small scale policies based on teams? Did I understand the question correct? Yeah. Yeah, I think at a production level, we used to have, in one of my previous places I worked, we had something called, we had a small microservice called like a compliance advisor service that was responsible for running the various Rego policies and ensuring that it used to be the central repository where all policies were managed. And at the API service mesh level, you could inject policies into a config map as needed, but that was essentially discouraged and done only on a case-by-case basis. Even from an entire CI/CD flow, once the CI flow completes, there would be a webhook that would call the compliance advisor service to ensure that the policies, say give you like an OK before you actually can deploy stuff. But I hope that painted a picture and gave you a feel of how things were set up at a scale of production.